video, we'll talk about eigenvalues and eigenvectors, some material that's probably familiar to you from when you first learned linear algebra, and the characteristic polynomial. So on this first board, I just want to start by giving you some definitions so that we're on the same page about notation. So an element lambda in a field F is an eigenvalue of the linear transformation T from a vector space V over a field F to itself if there is a non-zero vector, little v, in the vector space such that T of V is lambda times V. So in this situation, this vector V is called an eigenvector of T with this eigenvalue lambda. All right, well, what about instead of asking for eigenvalues and eigenvectors of a linear transformation, we ask for eigenvalues and eigenvectors of an n by n matrix with coefficients in a field. So let's say that A is our n by n matrix with coefficients in F. An element lambda in F is called an eigenvalue of A with corresponding eigenvector, little v, if V is a non-zero column vector of length n, so that A times V equals lambda times V. So it has to be a column vector of length n for this multiplication to even make sense. And this looks very similar. All right, so if lambda is an eigenvalue of T, you can consider the set of all eigenvectors in V which have the same eigenvalue lambda. So this set is all the vectors in V so that T of V equals lambda times V. So you have a space like this for each lambda. This is called the eigenspace of T corresponding to the eigenvalue lambda. Okay, what about eigenspaces for matrices? Well, if lambda is an eigenvalue of the n by n matrix A that has entries in F, then you can take the set of all column vectors of length n for which A times V equals lambda V, just like here. So the set of all eigenvectors of A with eigenvalue lambda, this is the eigenspace of A corresponding to this eigenvalue lambda. All right, so I'm going to pause and erase, and then I'll tell you a little bit about the relationship between eigenvalues and eigenvectors of a linear transformation and eigenvalues and eigenvectors of a matrix representing that linear transformation with respect to some chosen basis B of your vector space B. If we start with a vector space and a linear transformation, and we choose a basis for that vector space, we get a matrix. Let's remember how this works. Let's say B is a basis for V, an n-dimensional vector space over F. A linear transformation T from V to itself gives an n by n matrix A, which in the past we've called MBBT, but I'm just going to write A for now. So what about what we want to do is compare eigenvalues and eigenvectors of T and eigenvalues and eigenvectors of A. Remember, A now depends on a choice of a basis, but T doesn't. T is just a linear transformation. So there's no choice of a basis involved in defining eigenvalues and eigenvectors of T. So let's look at A. So A is our n by n matrix with entries in F, and V is an n-dimensional vector space over F. If you just start with a matrix, you can define a linear transformation from this matrix. So we have a linear transformation from V to V given by T applied to a vector is going to be A times V. This notation is a little informal. What is this? So this is an n by n matrix with entries in F. This is only going to make sense if this is a column vector with entries in F of length n. So this second V is going to be a column vector consisting of the coordinates of this vector V with respect to the basis B that we chose up here. So we've used this idea before of taking this vector of coordinates to express a vector in terms of a chosen basis. We've written this as bracket V sub B. Yeah. Okay, so you can see by just comparing what it means to be an eigenvector for a matrix with a given eigenvalue and what it means to be an eigenvector for a linear transformation with a given eigenvalue, that some v in your vector space is an eigenvector of t with eigenvalue lambda if and only if this column vector bracket vb, this coordinate vector of v with respect to this basis, is an eigenvector of this matrix A with eigenvalue lambda, meaning you start with this linear transformation, you get this matrix A, little v is an eigenvector of t with eigenvalue lambda, if and only if this particular vector that depends on a choice of basis is an eigenvector of A with eigenvalue lambda, where remember A also depends on this same basis. So I'll leave it to you to really check that this is true. So what does that mean? So the set of eigenvalues that you get for the linear transformation is the same as the set of eigenvalues that you get for this particular matrix A, but A depended on a choice of B. So what this is saying is any choice you make of a basis for your vector space V, the set of eigenvalues that you get is going to be the same. So the eigenvalues for the linear transformation T are the same as the eigenvalues for the matrix of T with respect to any fixed basis of V. So you start with the linear transformation, you have many, many, many choices of bases, you can get many, many, many matrices representing that linear transformation, but the set of eigenvalues that you get don't depend on that choice of basis. All right, so I'm going to pause and erase, and then I'll talk a little more about eigenvalues and determinants and similar matrices. We want to give some equivalent conditions for what it means for an element lambda in F to be an eigenvalue of a linear transformation T. And in order to do that, I first want to define the determinant of a linear transformation. We know what it means to take the determinant of an n by n matrix with entries in F. So what is the determinant of a linear transformation from V to itself? It's the determinant of any matrix representing the linear transformation. And I want to note that this does not depend on the choice of matrix. So there are many, many matrices representing the same linear transformation. Why do they all have the same determinants? Well, this is a good excuse to recall some things that we learned in 206B, and also some things that you know about determinants from when you first learned linear algebra that we kind of skipped over in 206B that are in section 11.4. All right, so first, a linear transformation is non-singular if and only if any matrix representing the linear transformation is non-singular. So let's remember that two n by n matrices A and B are similar if there is a non-singular n by n matrix P such that P inverse AP equals B. Why is similarity such an important concept? Because two n by n matrices A and B represent the same linear transformation T from V to V with respect to different bases if and only if A and B are similar matrices. So we start with a linear transformation from V to V. We want to say that the determinant of any matrix representing the linear transformation is the same. But what do all those matrices have in common? They're similar to each other. So we just have to see that similar matrices have the same determinants. Well, an n by n matrix A is non-singular if and only if the determinant of this matrix is non-zero. So we saw that an n by n matrix A is non-singular if and only if it's invertible. And in section 11.4, there's a proof of something that you know from your first linear algebra course, that a matrix, n by n matrix A with entries in a field now is invertible if and only if the determinant is not zero. Okay, so along with that discussion, just like for matrices with entries in the real numbers, the determinant is multiplicative. The determinant of A times B is the determinant of A times the determinant of B. This is theorem 28 in section 11.4. We didn't give a proof of this in lecture last quarter. I encourage you to check it out, but this is not something that you'll need to know the proof for this course, but you should be comfortable using this fact. So now, what do we need? We just need to see that the determinant of P inverse AP is equal to the determinant of A. And that's true because the determinant is multiplicative. So we have this is equal to the determinant of P inverse times the determinant of A times the determinant of P. And the determinant of P inverse is the inverse of the determinant of P. For one thing, you can, F is a field. These are all things in a field. You can, so this multiplication is commutative. You can write this as determinant of P inverse times determinant of P, which is the determinant of P inverse times P, which is the determinant of the identity matrix, which is 1. But in the end, we just see that similar matrices have the same determinant. So the determinant of a linear transformation really does not depend on the choice of matrix representing that transformation. Okay, so now that we've recalled some of this stuff, we'll give some equivalent conditions for lambda to be an eigenvalue of a linear transformation. We next want to state and prove proposition 12 from section 12.2, which says the following 3 things are equivalent. Lambda is an eigenvalue of the linear transformation T from V to itself. Lambda times I minus T, where I now is the identity linear transformation, is a singular linear transformation. And then the third one is that the determinant of the linear transformation, lambda times I minus T, is 0. Okay, so what have we seen already? The things that we recalled about linear transformations being singular and matrices having determinant 0 already show that 2 and 3 are equivalent. That linear transformation is singular if and only if any matrix representing that linear transformation is singular. So you can choose a matrix representing that linear transformation. You can choose a matrix representing the linear transformation lambda I minus T, and that matrix is singular if and only if the determinant of that matrix is 0. Okay, so we just have to show that 1 and 2 are equivalent. What does it mean for lambda to be an eigenvalue of T with eigenvector V? That means that V is a non-zero vector with T of V equals lambda times V. But that means that V is a non-zero vector in the kernel of the linear transformation given by lambda times the identity linear transformation minus T. So if there's an eigenvalue lambda, that means that there's a non-zero vector in this kernel of the linear transformation, lambda times the identity minus T. So this linear transformation is singular. That's what it means to be singular. You have a non-zero vector in the kernel. All right, so now we're ready to define one of the main things that we've been aiming at in this video, the characteristic polynomial of a linear transformation and the characteristic polynomial of a matrix. Let's say that X is an indeterminate over F. So it's just going to be like the fancy name for our variable. We take the polynomial determinant of X times I minus T. And this is the characteristic polynomial of T and is denoted C sub T of X. So that's the characteristic polynomial of a linear transformation. So we have this linear transformation, we take its determinant, we get the characteristic polynomial. So if we have an n by n matrix A with coefficients in F, we can take the determinant of X times I minus A, where now this I is the identity matrix. Here, this I is the identity linear transformation. The determinant of X times the identity matrix minus A is the characteristic polynomial of A, denoted C sub A of X. And okay, so A is a matrix with entries in a field F. X times I is a matrix that has X's all along the diagonal and zeros elsewhere. X times I minus A, now there are some X's, but there are also entries. I shouldn't say coefficients, I should say entries. There are entries that are in F. How do you take the determinant of such a thing? Just like you do the determinant of a matrix with entries in any ring, just treat your x like a formal variable and take the determinant. Okay, so I want to prove for you that similar matrices have the same characteristic polynomial. This is not stated and proven this way in dominant foot. It's very similar to this thing that we just showed, that the determinant of a linear transformation doesn't depend on the choice of a matrix representing that linear transformation. But this is like a really classical linear algebra argument, so I want to show it to you for sure. All right, so we want to show that similar matrices have the same characteristic polynomial. We have the characteristic polynomial of A is a determinant of x times I minus A, and a matrix similar to A is P inverse AP for some matrix P. So if we take xi minus P inverse AP, we can write that as P inverse times xi times P minus P inverse AP. Why can we do that? Because x times I is in the center of this ring of matrices. It's just got ones all along the diagonal, so it commutes with matrix multiplication. So if you put a P inverse on the left, a P inverse on the right, you could cancel those out. That's the same as just taking x times I itself. But this is convenient because now we can use the distributive property to write this as P inverse times xi minus A times P. And now we just have to take the determinant. We'll see that the characteristic polynomial of P inverse AP is the determinant of xi minus P inverse AP, which is the determinant of this product. And the determinant is multiplicative, so we get determinant of P inverse, determinant of xi minus A, determinant of P. But that determinant of P and determinant of P inverse cancel. So we get the determinant of xi minus A, which is the characteristic polynomial of A. All right, so I'll pause and erase, and I'll just say a few last things about the characteristic polynomial before moving on to the minimal polynomial in our next video. A few last things about the characteristic polynomial. If you use the definition of the determinant, expanding it out as this big sum involving the sign of permutation times products of matrix entries, you'll see that there's really only one way to get all of the x's to occur in one term in that sum. So expanding the determinant using the definition shows that if the dimension of your vector space is n, in the case that you're considering a linear transformation T from V to itself, or if you're thinking about an n by n matrix A, in either situation, the characteristic polynomial is a monic polynomial of degree n. What are its roots? Its roots are the eigenvalues of T, or in the case of a matrix, the eigenvalues of that A. Well, why is that? You're looking for values so that the determinant of lambda times I minus T or A is 0. And this is one of the equivalent things that we saw in that last proposition. In particular, we have this monic polynomial of degree n, and its roots are the eigenvalues. So this polynomial has at most n distinct roots. So there are at most n distinct eigenvalues for T or for the matrix A. So I just want to finish this video with a quick little example. If you have a 2 by 2 matrix A, B, C, D, what is its characteristic polynomial? Well, you take x times the 2 by 2 identity matrix minus A. So you get this matrix x minus A, x minus D, minus B, minus C. You take the determinant. I know how to take the determinant of a 2 by 2 matrix. It's this times this minus this times this. So it's x minus A times x minus D minus B times minus C, which you can write in terms of powers of x as x squared. It really is a monic polynomial of degree 2 minus A plus dx plus AD minus BC. And these coefficients are meaningful. This is something we'll come back to. We get x squared minus the trace of this matrix, the sum of the diagonal entries, plus the determinant of this matrix.